Hello guys, today I'm gonna review a work AudioLM by Google Research. The AudioLM is a framework for audio generation. So what is audio generation? It's similar to text generation, but you feed the model with a audio prompt. For example, 3 seconds of audio recording. Then the model is capable of autoregressively generating the rest of the audio or continue the audio. And these authors, they proposed a hybrid tokenization scheme. I think that's new to achieve the objectives. The objectives are to not only code or map the audio into a sequence of semantic tokens, but also map them into a sequence of acoustic tokens. I will explain what the semantic and acoustic tokens in the following recording. Please stay with me. And the authors, they have also shown that the model learns to generate natural and coherent continuous given short prompt. And also, it's interesting that the model is also capable of piano music generation, although the author have not feed the training with any symbolic representation of music, for example, chords or notes. I think the introduction, if you have subscribed my channel, Olewave channel, you probably are familiar with a lot of the paper they mentioned about. So I'm not gonna stay with the introduction today. For example, the W2V bird, I have a paper reading on that. So to compare with the previous work, the first thing they're doing with compared with is a hi-fi neural acoustic audio synthesis. WaveNet. I have not read the paper WaveNet, but I do recommend you to take a peek at it. It takes you probably less than 10 minutes to read it and to understand the neural network architecture. I think it uses a dilated DNN or CNN. And the major contribution of the WaveNet to the speech synthesis research domain was they introduced a classification approach to the synthesis. So before that, people are using not only using the concatenative based approach, but they're using the parametric approach, which is like the generative model. But WaveNet turned the speech synthesis game into classification game, or say before that you do have to have a signal processing knowledge, or using some type of a generative model which is fairly sophisticated to do the speech synthesis. But after WaveNet, it turned into model training. As long as you have pairs of training data, for example, text and speech, then you can start the training in the end-to-end style. WaveNet is by DeepMind. And then the authors do have, if you're really interested in this AudioLM paper, I do recommend you to take a close look at the SoundStream neural codec. I'm not going to read it today, but I will give you a quick idea of what it does. If you look at figure 1, you can see it, right? So you see the the light blue circle, but the box is about a sound stream model. So you see, it's very like a autoencoder, but the only thing different from a normal autoencoder is inside of between the encoder and decoder, there are layers of RVQs. RVQ stands for residual vector quantizer. So you see, the point of having these RVQs was try to provide finer and finer grained acoustic representations. And I guess most of you are familiar with the VQ, but you can definitely see that the output of each layer of RVQ is finer and finer. And later on, the intermediate output from the RVQ layers would be stacked together to form not only a vector, but also like a matrix or tensor. And they call these tensor acoustic tokens. Okay. Yeah. I think the main purpose of this is not to be like, for example, Hilbert or Wave2Vec 2, which would generate intermediate representations for lossy reconstruction, right? That's not what they want. But their source stream neural codec, the purpose was to generate targets for a sequence modeling task operated at a lower sampling rate, which can be later decoded back to audio at the original sampling rate. So the main purpose was to compress with less amount of information to be lost, not to preserve semantic information, but to throw out lots of the acoustic details. But indeed, I think if you look at the self-supervised learning of audio representation, I don't think this is very different from the first section, high fidelity neural audio synthesis. It's very similar. And the authors, they emphasize this again. Hilbert or Wave2Vec is trying to discover high-level representation. Okay. For example, phonemes and music notes and class labels. I do not fully agree with them because Hilbert, if you look at the output of Hilbert, you can hardly associate those output tokens with the phonemes. You do have another layers to map them back to phonemes. But I agree with them. It's a higher level representation. Yeah, and they are saying that if you mention the self-supervised learning model, you definitely want to talk about people who have done lots of work in the NLP domain. The main purpose was or people in the speech or audio domain, they borrow the methods from the methods people are using in the NLP domain. And why do they do this? The purpose was trying to discretization of audio signal into a finite vocabulary of tokens. So once you get the tokens or tokenized audios, so you can leverage the common NLP based methods, right? As long as you have tokens, you can do NLP things. But the issue was when people doing the quantization. Remember that in the Wave2Vec, I have a paper reading on this. Waveback 2.0. Just search in my channel, okay? You can see they are leveraging contrastive loss. Or if you check the CPC, contrastive predictive coding, I don't have a paper reading it. It's a very ancient paper. Those objectives, contrastive or predictive objectives, they are exploiting the long-term dependencies, and the model tends to give up modeling the fine-grained information of the acoustic signal, or to say they throw away some information that is not important to the contrastive learning. Eventually, I think the author, they would show this again. These type of learning, they are just benefiting the common discriminative downstreaming tasks such as a speech recognition. And those representations are designed for this. And this is the reason why the author, they proposed this AudioLM to provide another way of modeling the acoustic signal. So the representation they got, or the tokens they got, are good for speech synthesis, not for speech recognition. Generating natural signal with language models. I think interesting thing is they're talking about a neural language model. Nowadays, everybody is using neural language model or large language model. They are all neural language models. They are very powerful, but the thing is, for NLP, this is not a thing. Remember, suppose you're using transformer, the computational complexity of a computing complexity of transformer is what? O(n) square times t, right? This is the training complexity. And what does the n mean? N stands for the length of the sequence. Okay. But for NLP, this is your not more than 1,000 tokens. And for the speech, this is way larger than 10 to the 3. It could be easily above 10 to the 5. So, and you can see that when my n size or our speech duration grows up, and this computational complexity will go up quadratically, right? As they mentioned. This is bizarre to training and also inference. Inference will be slow too. So this is why the authors, they say they want to explore new methods. Okay, this doesn't make sense. I think some people, they do the autoregressive transformer. I don't have a paper reading of this. You can just Google or AR transformer. But in this way, I think the computational complexity can be reduced because the prediction of the transformer are then mapped back to the original signal space. I don't have time to explain this, but this is a general concept of reducing the complexity of generation. Okay. For audio, they mentioned about reconstructing music, jukebox. What I have to say that this is I'm not very an expert in music generation. I mostly work on speech. GSLM. I do recommend you read this paper, GSLM. GSLM was very successful according to the text. And they're saying that this GSLM shows high temporal coherence. What does that mean, temporal coherence? It means although the GSLM doesn't have any labels of semantic or syntactic information in the labels, but the audios they generated from the GLSLM, actually their spoken language generated by it, is quite meaningful, which is interesting. That means the model is capable of capturing some semantic information from the raw signal. But you definitely see that the jukebox, they showed some significant artifacts. That means I think later on they mentioned that when there are lots of artifacts there, that means the model captured the semantic information, but this throw away some important acoustic information. This is what you can see that you might have already got some idea of what the authors they want to do. Definitely there is a trade-off relationship between modeling or keeping the long-term coherence, and also between the high quality speech synthesis. And the author they did this by they alleviate the trade-off issue between these two factors by combining the semantic information. The semantic information is mainly for tackling this issue, okay? The acoustic token is mainly for tackling the high quality issue, but they combine these two. So they're saying that, okay, we can address the trade-off between these two problems more efficiently or effectively. Okay. And that they have said that their model has an advantage over GSLM, and I think they basically, the idea is coming from GSLM, but it's improved upon GSLM, because they can generate a speech continuation that preserve important thing, okay, that preserve the original speaker's identity and the intonation, and by the same time they can also extend audio continuation beyond the speech by generating piano sequence. Yeah, I think GSLM it will not be able to generate a speaker specific speech, because I think I mentioned that GSLM is only limited to a single speaker in a clean setting. Okay. The model wise is very straightforward. I know some of you guys like to check the model, but the model is very, very straightforward, I would say. First of all, during training, you got a raw speech here, and the raw speech on the right side and left side, they pass through this sound stream neural codec. Like I just mentioned, sent to the encoder, pass to the RBQs, and get to the decoder. Decoder, it tries to compare it with this original speech, was in a certain type of loss function calculation, right? Then it's able to train this decoder, encoder, and the RBQs. And the intermediate layers they got acoustic tokens. Okay. At the same time, they also train a W2V BERT. For those of you who do not know what is W2V BERT, it's easy to understand. I think it's training from scratch. On the yellow box section, there is an encoder, or you can call that self-supervised. There's the encoder, or the SSL, self-supervised learning model, or pre-trained model. Okay. And on top of this, they have a decoder. I'm really sorry. think on the decoder they have some type of mask language model decoder, right? Something like this. But I'm really sorry, I may have a wrong drawing. But the W2V bird, the main idea is it trained a encoder and decoder from scratch. The encoder is trained in a contrastive loss, and the decoder is trained in a CE loss. And actually, the two losses are combined together in a weighted fashion. That's the general idea of that. But you can see that W2V bird is trained using the CE loss, you see, or the contrastive loss. CE loss plus contrastive loss, which means that it's designed for the classification purpose or ASR purpose. The downstream task can be ASR, speaker ID, emotion classification. You can see that once you got the output of the model, they can cluster the output vectors using k-mean, and they are capable of converting the output vector into semantic tokens, right? Versus the acoustic tokens obtained by the sound stream neural codec. Okay, and remember this. Although they draw this in the same graph, but I don't think they are trained. You don't have to train them together. I think it's separated. Okay, makes sense. Okay. Trade-off of discrete audio representations. I think I have explained the trade-off between these two, right? Between these acoustic tokens and semantic tokens. The W2V bird stress on the semantic, but the soundstream stresses on the acoustic. Okay. You may be confused with 200 bps. Well, this is simple. This means it's 50 hertz times 4 beats. It's coming from this is 2 to the 10 bits, then times 4 layers. Okay, that's the meaning of 200 bps. Another question is, do you think the soundstream neural codec is lossless codec or lossy codec? Yes, it's a lossy codec. Any neural codec is lossy. Yes, they're mentioning this again. Interesting thing is they actually normalizing the W2V bird embedding so they can get better performance. Interesting. This is important. Or this is worth noting that they appreciate other people's work, right? The way of they cluster the output of the W2V bird is similar. Actually, it's the same as how people obtain the tokens in the Hilbert. And I do have a paper reading of Hilbert. Search that in my channel if you want to read it. It's very straightforward. I think you should read it. Hilbert. It's try to tokenize the audio try to tokenize audio, okay, or speech. So afterward, you can play with the NLP based methods. Talking about some analysis, First, they measure the phonetic discriminability in terms of ABX error. It means whether these two things can be confused with each other, right? They're saying that the smaller the number, the better the algorithm is. You can see whenever you increase the bit rate for the two methods, this is method number 1, this is method number 2. If you increase the bit rate, that means your model size gets larger. You can always reduce the phonetic discriminability. Okay, and the within and across means that the two utterances are from the same speaker, and across means that the two utterances to discriminate the phonetic are coming from two different speakers. Right? It seems that across is more difficult, right? Makes sense. But what can you see from here? You see, if you're using the acoustic tokenization method, soundstream, neural codec, their phonetic discriminability is way worse than the semantic-based tokenization. And also, when you come to the reconstruction quality, what does that mean? I think they're using some sort of a Vice QOL unit method. It's a more like objective evaluation. So the larger the number is, the better the quality is, right? So you can see this is good, right? And then see this is better. So you see but if you're doing the reconstruction purpose or for the TTS purpose or speech synthesis purpose, you should definitely go with the acoustic token. See this? So you can see there is a trade-off between semantic and acoustic when you try to code the speech or tokenize the speech. That's the trade-off. See, you cannot get both. Yes, that's the word of the author. Consequently, achieving both high quality and long-term consistency with only one of the tokenizer is challenging. This means the trade-off. Here, I think we finally come up to equations. I think this is some argument made by the authors. They're suggesting that semantic token would ensure long-term consistency, but while the acoustic tokens would ensure high-quality audio synthesis. So this is the two things are the foundation of their proposed method, because if you agree with them, then the AudioLM framework they propose is very natural. Okay, and they propose something called a hierarchical approach. They first model the semantic token, and then use that as a conditioning to predict the acoustic token. That's the main thing of the acoustic model, or the take-home message. First, they model semantic. Then the condition on the semantic to predict the acoustic tokens. So what exactly they do? First, semantic modeling. This is easy to understand, right? If you're very familiar with GPT model, you know what this means. The history, you're giving history, what's the next semantic token? And then what they're saying that they're doing the coarse acoustic modeling. You can see this equation. I don't have to see the text. The equation is very clear to me. So Y means acoustic token, right? And the Q means, remember the RBQs? There are several layers of RBQs. So the course of, so suppose in total there are 1 to Q layers. And this is only up to Q prime. So suppose there are 1 to Q layers. And this is from 1 to Q prime. Fourth layer is only up to here, right? Doesn't contain all the layers. And the output of the certain layer is Q, right? Then at time T, so what's the next acoustic token at layer Q? Given the semantic token, then you can see given the semantic token Z, it doesn't have T, that means you have all the semantic tokens from 1 to T, right? But you can see this Y, but you can search, you definitely, the prediction of next acoustic token is based on history. So the history wise, it's based on the acoustic tokens that were in the history, less than T, and from all the layers up to Q prime. Make sense? And also, you can also, because you're predicting the Qth layer, right? Any layers before Q. Remember, this is, say, this is a neural network, right? And this is the decoder. This is the encoder. And this is a layer 1, 2, blah, 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 Q. So say this is layers Q, right? Okay. But any layer before Q can be used to predict the layer Q. So it has two-dimensional things, right? Not only the time, but also the layer ID. Makes sense? Then you're capable of getting what? Getting this. What is this? You see the figure 2? That's this part. I will draw the blue part is here. And let me draw the red part. This is a semantic token. This makes sense? You may ask, what does it mean by Y2 and Y1? Because they're saying this, the factor 2 comes from the fact the sampling rate of sound streaming is twice as of a W2 Weber embedding. So there's 2 times tokens of acoustic compared to the semantic tokens. Okay, then it comes to the third stage. This is stage 1, this is stage 2, and then goes to the third stage, fine acoustic modeling. In this stage, you're still trying to predict the YT to Q, but this time you see the Z is gone because they're saying that in this scenario, the fine acoustic tokens are no longer dependent on the semantic tokens, and that it only depended on the coarse acoustic tokens. Let me draw this. These two how to say this? These two parts are the coarse acoustic tokens. Are you with me? These are the tokens less than Q, right? From all the time. But I think this is more like coarse acoustic tokens. This section, especially this section, is a history you see. This is a history of the fine token. This is a history of the fine acoustic tokens, but it's for the layers above. Remember, I have the layer this, the layers above. This is Q prime plus 1. This, right? You see all the layers above Q. This is for fine acoustic token generation from here. They're all from here, and also at the time t, you can definitely, it's similar as this one I explained. These two are similar, right? Same. You can use the time, the y at the time t, but for the layers less than q. What do I mean by q here? But this way, the q is greater than q prime, but this q is different than this q here, right? This q is less than q prime, but this q is greater than q prime. I hope you understand this. And then you can see that for the fine acoustic modeling, you can see this part is, like copied here, and then it's capable of generating this part. So you see, step 1, they get this. Step 2, they use this to get this condition on semantic tokens. And for the third stage, they condition on the coarse acoustic tokens to get the fine acoustic tokens. And eventually they throw away the semantic tokens. You see, they combined the coarse and the fine acoustic tokens, and they fed this combination into the sound stream decoder to get the speech. You may ask, why do they throw away the semantic tokens? They have to, right? If you look at the sound stream neural codec, it's the decoder which generates the speech. But the decoder only uses RVQ output, so it has to be acoustic tokens. So the semantic token cannot be used in the cannot be used in the sound stream. So just want to emphasize that again. The semantic token is like intermediate result that will be eventually be discarded. It only be used as a condition for generating these acoustic tokens. And they have done some delicate thing. The meaning of this, they actually means in order to make sure that on the stage 3, fine acoustic modeling, the modeling can be focused on the fine acoustic characteristics. They chop the audios into shorter chunk. Why do they do this? So they do not want the model to model the long-term context, because if the model is forced to learn this long-term context, it's very probably to learn these semantic tokens, semantic information, which would probably ruin the fine acoustic token learning. Yeah, that's what they actually mean. That means they're using more residual quantization Q to achieve higher quality. I think the third stage is very smart. And you may ask, why do they do this in threes in a hierarchical style other than just to do all of them together? I think they mentioned this. I think they also forgot where they mentioned this. There are two reasons. First, they're saying that they regard the fine acoustic token to be conditionally independent from the semantic tokens. There's no reason to combine these three to be learned together. Well, the second thing is, yeah, they are like what I just explained. They're more locally dependent on the coarse acoustic tokens, right? Like shown here. This depends on this. This depends on this. All right. And for the inference, there are three styles of generation. The first is unconditional generation. This is mostly the purpose of generating semantic tokens. What do they mean by generation? So it's given an audio, then using the audio prompt to, then you tokenize the audio prompt, having a sequence of tokens. Then you use these tokens for generation, okay? And then, but the way you generate the tokens are different, right? You can either using a semantic tokenizer or acoustic tokenizer, like shown before. Acoustic generation. Yes. I think this is just to go from semantic to acoustic. And the third one is the key of this paper, generation continuation, which means given the short prompt, they do the same thing as they do in the training. They first get a semantic focus, then they got the coarse acoustic tokens, then they got a fine acoustic token, right? Hierarchical style inference. Experiment. They played with a speech continuation and a piano continuation. Dataset. I think the previous work, some other work, or maybe they have done something previously, they use 6,000 hours of a clean subset of a Libre Lite, but later on they found that if they use a full data set, which is 60,000 of hours, they can get stronger results. Yeah, the parameters, I will skip them. This is important. We sample the acoustic token based on the ground truth semantic tokens extracted from their original samples. But this is the basic of their settings. This is the basic their setting of settings. Okay. I think their experiments are very easy to understand. What does the table 2 say? They're playing with on the Libre speech test set or some test set, and they're doing the speech recognition on the generated tokens. For the original speech, they can get this and this. But say they do the same step as they did before, using the ground truth semantic tokens, the generated acoustic tokens, they can get very good result. That means the reconstruction was very successful. When they're using the AudioLM, oh, I'm sorry. Reconstruction with a sound stream was the previous method. Okay. People propose in the sound stream method is purely this. It's purely acoustic tokens. But for the AudioLM, it goes from semantic to coarse acoustic to fine acoustic. Then they combine these two to generate audio. They're saying this result is okay, but also said this is good. I guess it is saying this is good compared to the JSLM. They're saying this AudioLM preserved the semantic information. So the ASR is to test whether your neural codec or your algorithm can preserve semantic information. Preserve semantic. Okay. Then what is more important is let's check the table 4. Okay. Swaggy is what? Swaggy is Swaggy is new to me, and I don't want to read it. You can just check it. Okay. Whether two similar sounding word, but the two similar sounding word for the two similar sounding word and a non-word, whether the model can give a higher probability to the word. And the S-blip means this is another task. Okay, this is task 1. This is task 2. Whether the model can grammatically correct a sentence. How do you see that? Oh, given two sentences, whether the model can give a higher probability to the grammatically correct sentence. For example, this one should have higher probability, right? The higher the number is, the better the algorithm is. The all and the in vocab means, because this is a Libre speech test, the author say, I want to see if the training set has seen this word before. That will be an in vocab test, and the result might be higher. The all means that everything, right? But the result might be lower because there is some out of vocab words in it, which is more difficult for the SWOGI task. Text-based top line, which means they have transcription. They can leverage the phonetic information to help with them. That's fairly easy compared to the case that you do not have a transcription. You can only use the tokenized the information to determine whether the word makes sense or not, right? Or it's a word or a non-word. And then what does the non-causal mean? That means, because they're using, you see that they're using the BERT method, right? BERT is, B means bidirectional. It has to look at the future to have a correct prediction of the current, right? So that means it cannot do generation. Why? Generation is always going from left to right, right? You cannot see the future. Future would not be visible to the current prediction. So that's causal prediction, right? Which one is more difficult? Well, I think the causal is more difficult, but these authors, they get better results compared to non-causal. See? But for the other method, this one is worse, right? Worse. But for the author method, they're doing better. You can ask, can the AudioLM do non-causal? I think you have to modify it, but I think the authors are not interested in, because they're doing the purpose of AudioLM is similar like the large language model or the GPT model and the NLP. They're trying to generate audio, okay? So it has to be autoregressive or causal. Split, same thing, right? It's getting better. That means what? That means the AudioLM is better than the other two methods, including the JSLM, in preserving the semantic information or the semantic tokens, or it generates better semantic tokens versus JSLM and other reference 62. What does the table number 3 mean? It means to check the speaker classification. Remember they talk about JSLM? JSLM is just synthesizing one single speaker's speech. It throws away speaker characteristic. Okay, but say you want to synthesize speech or continuing generation of a voice prompt or audio prompt. You want to preserve the speaker characteristic in the generated speech. This is why they're doing this. First of all, if you're just playing with their previous method, reconstruction with a soundstream neural codec, you can get 100% speaker classification. It seems that's a resolved problem. But this one, you do not preserve the semantic information in a good way. I think they might have some results, but it's interesting that I didn't find that in this paper. Yeah, this is why I think should they have a sound stream results here to give us an idea of how the sound stream, which use pure acoustic token and not condition on semantic token, can perform. I wouldn't. It's okay to me that this result is very, very bad, but I think they should have a comparison with the sound stream based method. Talking about this, I mean, this one you got very bad speaker classification result. You see the audio generated from ground truth semantic tokens. This is like a, well, I have to say that it's a little bit confusing to me, because definitely you see the AudioLM. You can see the AudioLM is eventually a combination of coarse and fine acoustic tokens, which were conditioned on the semantic tokens. But here they're talking about the semantic tokens. But I understand what they want to say, that if you tokenize the audio in a semantic based method, you're not gonna preserve the speaker characteristic, and your classification rate of the speaker would be very low, but it's slightly higher than random guessing. I think they're talking about the random guessing. If you do random guessing, you will get 0.3%. It's slightly higher than 0.3. But if you're doing the continuation or the method they mentioned in this paper, you're gonna get a fairly high speaker classification accuracy, which means the speaker characteristic is preserved in this method, which is important for them to generate a specific speaker's voice, right? And they do perform subjective evaluation. The evaluation is done in this way. They have human raters, and the rater would be assigned to a recording. The recording is exactly 10 seconds, and the question was, is it a original recording of the human being or a synthetic continuation speech? And to perform the speech continuation, they use a prompt of 3 seconds, and they generate the subsequent 7 seconds. And those 10 readers screened for proficiency in English. They didn't say whether they are native speakers. Yeah. This is, I think, not very satisfying to me, because you do have to want to point out that, make sure that these are native speakers of English, because English is my second language. I I wouldn't be able to distinguish synthesized speech from natural speech very well. So the subjection evaluation would be focused on 3 properties: semantic and the syntactic correctness, the acoustic coherence. You see, this is semantic, this is acoustic coherence. The third is the generation artifacts. They're saying that it's interesting to me. After they collect 1,000 ratings, they say for those raters, the successful of assigning the correct label is only 51.2. And the p-value is 0.23, which is suggesting that human beings are struggling in differentiating the speech samples from synthesized speech. Does that mean the algorithm is really good? I personally think that they should have more experiments or have more raters or show the breakdown of those numbers. How do people think on these 3? Because you instruct them to use these 3 criteria to judge or train them with those 3 criteria. And we definitely want, or the readers, the readers would definitely want to see the breakdown of these numbers, right? But it seems that that result suggests that the algorithm is pretty good, because they're saying that human readers are struggling to differentiate, synthesize the speech from the real speech. And also, pause the video to see if you can ask a question here or find the issues in their experiment. Right? They should compare using the same speech reader on the GSLM synthesize the speech, because definitely the GSLM can do the speech continuation. Because I'm questioning the meaningfulness of the 51.2, because I think people can do better job than this. But if you have a number of on the algorithm of a GSLM, that would give me a better sense of how people are doing. Okay, I mean, even those people are not very capable. For example, suppose some of them are not native speakers, but seeing whether they can do well on GSLM algorithm would also give me an idea of how the algorithm is compared to other algorithms. Because you can definitely compare the human performance versus your you definitely just compare your algorithm on human performance, but it would be nice or convincing to show your algorithm's advantage over another example, GSLM. But I think they do mention that GSLM is just for single speaker speech synthesis. That means the speaker characteristic is thrown away. So maybe not GSLM. Probably the reference 63 or some vanilla autoencoder, right? Or some autoencoder. Can they do this? Or maybe SoundStream. Yeah, SoundStream might be very bad in doing this, because I don't think they can do semantic thing correctly. Okay. Piano continuation. I don't think the author, they want to spend a lot of things on this. They only say this is preferred by 83.3. Jeez, this is doing way better than. This is doing very well, but I'm not a music expert, so I would just skip this part. And they do have mentioned the broader impact, which is the ethical thing. The first thing is that the first concern was social bias. Okay. And also, they're also talking about underrepresented group in the training data. But you know, these type of things, sorry, being cynical here, it sounds like this part is written by their corporate legal team, not by the authors. So it's very hard to understand this for me. The conclusion. So they propose the AudioLM framework. They can provide a audio generation which preserves both long-term coherence, which is semantic, and also high audio quality, which is acoustic information. And remember, this is AudioLM is autoregressive, which is same as GPT. So this is a causal. It can do left to right synthesis or do the continuation generation. And what the future work could be. They're saying that this can be extended to other types of audio, for example, multilingual speech. Say, is that possible for the model to, you give a audio prompt of English, then it would continue to speak the sentence in French? Polymorphonic music. Yeah, I don't want to comment on that. An audio event. And interesting. Well, yeah, once you plug this thing into a encoder decoder, you can definitely use this to in a task which is text to speech. How do they do this? I think what they actually meant was just keep feeding, or not keep feeding. So the encoder. So this encoder would take all the text in, and they got a text embedding, and the text embedding, they can either plus a empty speech prompt, okay, and then these two things together would be fed into their AudioLM. I think the AudioLM might have to do something, change something. For example, how did they add the extra text embedding into it? Audio embedding, and the output is audio embedding because it sends through a decoder. Yeah, and then would generate the speech. I think if you are familiar or watched my paper reading on the Wall-E by Microsoft, you would definitely find that this is the idea of Wall-E. Okay, Wall-E is a text-to-speech, but it definitely for the Wall-E, and this part is not empty. It's a speech prompt, speech of 3 seconds or 10 seconds, 3 or 10 seconds of speech. You can see definitely these two things together, text embedding and the speech embedding all together, got to be fed into the AudioLM, and it would synthesize speech with content, but also with the speaker characteristic of the voice prompt. Okay, also speech-to-speech translation is easy to understand. For this graph, you just throw away the text embedder. You just send the speech as input, or what I'm thinking speech-to-speech translation might be like this. The encoder, they send the speech as input, and they got a speech encoder, and they plus some empty speech of the target language, okay? And then send it to the AudioLM, and they got the target is the source speech embedding. This is got target speech. The target speech can be French, and the source speech can be English. So this is how they do. I think this is what they're trying to do with the speech-to-speech translation. Okay, finished. How do you like my paper reading? Please don't forget to subscribe if you do like it, and share that with your friends. And see you next week.